Alrighty guys, so what we're going to do is we're going to talk about the second part of the energy concept map, and that would be what do we do with work once we've graphed it. Once we've able to find it algebraically, understand what work is the system, we're now going to graph it. So the next part down here, if you're writing along with me, would be to include how do you talk about work done graphically. That's typically done with a force versus displacement graph. And let me clean that up just a little bit and get some straight lines drawn in there. So what I'm going to do is see if I can figure this out. There we go. Let's get some straight lines drawn in here. That way, when I talk about this graph, we don't lose what's going on just because my very poor drawing style came into play. Alrighty, so now I have force versus time. Force versus distance. So we have force on the y-axis, and we have displacement or distance on the x-axis. If I were to have a graph that looked like this, what could we say is going on? Well, the first thing we would notice is that the first chunk of time here, we'll call this a positive time. We have some positive force and positive distance, and so the area under the curve here would be a positive force times positive distance. So the work here would be positive. And that'd be force times distance, because the area of a square would be length times width, so it'd be d times f. The next part we'd be looking at would be this next chunk right here, and this is a triangle. So to find the work done in the system right here, it would still be positive because it's a positive force in the distance, but the area of a triangle would be 1/2 distance as my base times force, which would be my height. So the area here would be 1/2 base times height. Now the other part would be if I said this triangle and this triangle were to be equal and opposite to each other, this work done here would be negative, and that'd be 1/2 distance times a negative force. And so if these two triangles are equal and opposite to each other, this work would cancel out, and we would say net work done on the system, net work, would be equal to the green work done plus the purple work plus the negative of the red work being done. And this purple work and I guess pink and red would cancel each other out, and saying the work net done on the system would be just this green portion right here. Now let's explain it. If I had an object, let's say starting at rest, it would be having a positive work done on it for some time, so it'd be speeding up, velocity is increasing, and velocity would still be increasing to this point because there's still a positive force on it, just not as much. At this point, now that force is now going opposite direction, and that means it would be experiencing a negative force. So it would be speeding up, speeding up still, but not as much, and then would then experience a negative acceleration and start to slow down. As far as graphing work goes, anytime you see a force versus distance graph, you should be good on that. As far as the next part to talk about would be what are some examples of work that cause negative work, and that number one rule or number one thing would most likely be friction. So one thing to note, friction usually causes work, and that usually causes negative work. So a negative work to be done. And remember, friction is calculated by mu sub, usually going to be mu sub k because your objects are already moving. So kinetic friction times force normal. And You can then break force normal down usually, and that's almost all the time going to be weight. Sometimes it'll be weight perpendicular if your object's on a slope. So what does that look like? If your object is, we'll say, experiencing friction on a flat surface, you're going to use this formula right here. However, if your object, say, had a frictional force of mu sub k force normal, that means your object is going to be having a weight perpendicular. And that's because friction here is going to be a component of your trig triangle here. And so, actually, it's not weight perpendicular, it's to be weight parallel. Weight parallel. All right. Oop, I'm sorry, that is correct. Let me erase that. Force normal would be equal to weight perpendicular. And weight perpendicular would be going up, while force normal is going in that direction. What I'm going to do, though, is I'm going to hit pause on this video and clean up this image. And actually, I think I'm going to re-explain this image here in a second. Alrighty, let's try this again. What we're going to do is I'm going to draw this object at an angle. Let's make it green. And so what I have here is mu sub k force normal, and that's going to be equal to weight perpendicular because weight's going to be going straight down. Weight perpendicular, or your component of weight, is going to be what's going to be equal and opposite to force normal. All right, I'm going to hit a pause on that and call this the end of part 2. Next thing I'm going to talk about is power and how power plays a role in this system and on your test.